Good evening. Can you listen to me? Great. Thank you so much for being here. I'm really excited to be talking about seeing the invisible universe and tell us how we explore the cosmic origins of our universe. And I always like this to start these talks talking about, what you see when you see the sky with your eyes. But if you have the best eyes in the world, you would actually see something like this. This is a real image taken by the Rubin Observatory in Chile. Almost everything you see in this image corresponds to a galaxy. I don't know if we can turn off some lights to have this, better. There's only, I'm gonna point here with my cursor, there's only a few stars here. You can tell because of the pattern here. Excellent. This is an image taken by an observatory located in the north of Chile. And as I said, almost every point here corresponds to a galaxy. There's only a few stars here, and you can tell, as I said, from the pattern. But importantly, the observable universe, in other words, the universe we can observe, we estimate there's 200 billion galaxies, and each of them we estimate has approximately 200 billion stars. So you can imagine, how vast and big is the universe. But this steady image of the universe is actually not what is going on through cosmic history. We actually see things moving. And in particular, this is a simulation, of course, the universe is expanding. And we know that because we see galaxies that are moving away from us or from the observer point of view. But in particular, this talk is about the cosmic history and our origins. So I want to show you now an image that shows this history. And you probably have heard that the universe comes from something called hot Big Bang, and that is expanding. And we know that because we see galaxies, and if we're not in a special part of, the universe, that means like everything is moving away from everything. And usually people, when they show this, a lot of people, when they see this image, because, we're humans, we go along the timeline. We start from the moment zero until now, and we estimate that the universe has 13.8 billion years. It's hard to, think of all the processes that went through. So before I actually go from left to right, I want to do an exercise and go from present to past. And the only thing we know from the talk already is that the universe is expanding. So in the past, the universe was more contracted. So we can try to do an exercise of grabbing the whole universe and compress it. And when we do that, different things happen, including the pressure goes up. Like in this box, I have particles. They're bouncing in the faces of this box. And when you compress it, this pressure goes up. Like when you have a pressure cooker in your house, you can go to really high pressure, and therefore, when you go to high pressure, you actually get higher temperatures. So if we compress the universe, pressure would go up. So imagine you're grabbing, again, all the galaxies, all the particles, or the planets, or the stars, and you're just compressing it and compressing it and compressing it. And then temperature would go up, and eventually it would shine. Because like when you have a metal and you heat it up, it starts to glow. So if we really, really, really compress the whole universe to really, high pressure, as I said, temperature will go up, and then you'll have something that will shine. And that's actually what you would get from theory. And in particular, if you sit down, do the calculation, okay, I grab the whole universe, these 200 billion galaxies with 200 billion stars on each, in average, and you compress it approximately 1,000 times, something really special will happen. The average temperature will go up to the average temperature we have right now. So if you go in a space, rocket, and you leave the Milky Way and you have a thermometer and just measure the average temperature of the universe, you'll get that it's approximately minus 270 Celsius, which in Kelvin, you might have heard Kelvin way of measuring temperature is approximately 3 Kelvin. But if you compress the universe actually 1,000 times, approximately, the average temperature of the universe will raise to 3,000 Celsius. And when you do that, that's, again, if you compress it, that's actually the moment where the universe is so hot that as a metal, it will shine. And it would actually emit a yellow, orange-ish light, like, oh, this is a bit white. in my screen looks more yellow, but it's like when you go and buy a light bulb in the supermarket, and there are different temperatures associated, like here. And that's actually, the color that, in theory, the universe would have if you compress it 1,000 times. Again, this is all theory. Let's try to prove it. And if indeed the universe back then was, emitting this light, in a universe that is expanding, light goes through a really interesting effect called redshifting. So if you have, light traveling, let's say, from a galaxy through a universe that is expanding, what will happen is that its light would stretch like an accordion. And this is part of, thinking if the universe is expanding, the light should change its frequency. So if originally the universe was so hot that was emitting this orange-ish light, we wouldn't receive orange anymore. And as I said, you can do these calculations because this is physics. And actually, I'm going to do them now. I'm going to derive them. No, it's a joke. It's a joke. And not going to do it because someone did it before me, and actually it was a Canadian. This was made by James Peebles and, of course, other amazing scientists. And James Peebles actually got the Nobel Prize in 2019 for his work on this field. And this is actually supposed to make you laugh. Great. That's the laugh I was waiting for. And he did this calculation. He was like, okay, if the universe, the universe is expanding, we compress it, temperature goes up, it should shine. But then the universe, when this shines, the universe expands. So the frequency of this light should change. So we studied that rainbow and how the light changes. So as I said, the light has some frequency, and you can think of it like, this wave that goes up and down, and it's like an accordion because the universe is expanding. And if originally that light was more or less on the visible, like orange, if the universe expands 1,000 times, it should actually move to this regime, to the microwave, and lower the temperature to the average temperature of the universe, 3 Kelvin. But you may be wondering, like microwave, like the one in my house? Yes, actually microwaves are, when you put food, you're actually, just illuminating it in light that is not visible, but is in the microwave regime. And that's why the pizza is horrible. Because you're breaking the water molecules, and that's why you should put the pizza in the oven. So this is the same light that you can't see with your eyes. That's the same light that is coming from when the universe was compressed 1,000 times. And this, as I said, was theorized by an amazing Canadian, and was observed in 1960s. So in 1964 in particular, Arnold Penzias and Robert Wilson near Princeton in the US, they detected a really strange low frequency signal in New Jersey. Sorry, I'm not native in English. And they were like, okay, they turned on this antenna. They were actually in the communication world. They were not doing science directly. And when they turned it on, they were receiving this background noise. And they were like, what is this? We can't, what is going on? And they were like, it's a couple of pigeons. And so they took them out in a really I think I've heard they killed them, but they took them out, and the signal was still there. And they're like, what are we detecting? And they were detecting the light from, the early universe. And that's when they all got the Nobel Prize, including James Peebles, because they discovered that indeed the fact was compressed in the time back many billions of years ago. And I'm going to be talking more about that in a second. And they detected that this was the signal, the first signal ever emitted by our universe, not by stars, not by galaxies, but by the fact that you compress the universe, and as I said, it gets hot. So right now, when we observe this light, it looks something like this. This is a full sky image of this light that, as I said, is in average at minus 270 Celsius. And the thing here in the middle is the Milky Way. And this was an image taken in 1964. And of course, you know that since the 60s, there have been a lot of development in astronomy. And one of the first space missions was the COBE mission to study this. And they had much higher resolution. And they were able to study these tiny, tiny temperature variations in the 90s. And then they had WMAP, and voila, 2015, one of the latest full sky observations of this light. And as I said, this thing in the middle corresponds to the Milky Way. And if you want to study what happened in the origin of the universe, you want to go farther away. So you took it out, you take it out. If you're someone like me that wants to understand the origin of our universe, and voila, you get something like this, which is called the cosmic microwave background. We call it cosmic because it comes from the cosmos. Microwave because we detect it in the microwave regime where the light has this particular frequency. And background because it comes from, the background of our universe in every direction. So another way of saying this is again a full image of the sky, and we see these little temperature variations. The average temperature, as I said, is like -3 Kelvin, -270 Celsius. And if you go out to the woods and you put your goggles to see the microwave sky, this is what you will be seeing. So as I said, I showed this like 2D projection, but it's actually the sky. And it fills the whole observable universe in a nearly homogeneous way. So if you go in every direction, there's not like any particular special direction if we take out the Milky Way. And if I go now back to this image that shows the history of our universe, this is mainly telling us that we started from a hot Big Bang, this inflationary period that my colleague Fiona is going to be talking more about. And then the universe expanded really fast, temperature goes down, particles collapse and create atoms, and then it will release this light called the cosmic microwave background. And then after that, there's going to be a dark age. Things will collapse. We're going to have the first stars eventually, the first galaxies. And, 13.8 billion years after, we're going to have our current universe. And this light was actually emitted when the universe, if you do the math, when it was 380,000 years old. And not only when you do the math, also when you observe it with this data. If I go back a bit to this image, I was telling you that these are like tiny temperature fluctuations. So, when you're on Instagram and you take a selfie and you like increment the saturation and you get like the redder's more red and the bluer's more blue. We do that here because we want to study this what is the physics behind of this. So as I said, the average temperature is -270 Celsius. It's actually this number. And the minimum temperature showed here in this color map, it's just, the difference is just here. That's what I meant with really low temperature fluctuations. And when you see the maximum here in the color map, is only this tiny difference. And that's why we say it's like it's super homogeneous. It's just we exaggerated like a Instagram picture to see this information. And Fiona will talk more about this, but like the redder spots represents particles of light that have a bit of higher frequency, and the blue ones a bit lower. And this is really, amazing that we can theorize it and we can predict this. But as I said, the distribution of these dots or this light is really important to understand the physics of the universe. So in particular, the distribution of these dots can tell us about, for example, the geometry of the universe. What do I mean by geometry? Let's say you go to the South Pole and you're a penguin, and you have another penguin, and you're like, bye, I don't want to see you again. So you go in opposite directions. But because you're on Earth in a sphere, you're actually going to find them in the North Pole. So even though you went to opposite directions, you're going to find yourself again because there's some curvature. And this is exactly what we're showing here. If the universe has some curvature, you might find yourself with another, penguin if you go in opposite directions. And that is linked directly to the distribution of these like dots that I was telling you. And actually, this data was part of a balloon that a professor from here, from UofT led, Professor Dick Bond. So you can actually, meet one of the leaders of this science here in Toronto. So it's great. This is just a brief overview of, this amazing cosmic microwave background. But I want to tell you more about the state of the art and the reason why with all these astronomers are actually here. Or I should say cosmologists, because we study the cosmos. So the state of the art right now is that if you zoom in to this data, you'll find that the resolution is not the best. So we need bigger telescopes, really big telescopes, but it's really hard actually to observe this because, as I told you, this is like when you put your pizza in the microwave, it interacts with water. If you have clouds, the light of the early universe is going to interact with the clouds. So what you want to do is to avoid also the atmospheric opacity, or in other words, avoid to have the atmosphere opaque to this light. So you can go to space, and in particular, the cosmic microwave background is more or less here when you study the wavelength of the light. So it's like in this sweet spot that, the opacity is not that bad. So if you go to a hill, you can try to, get less atmosphere and try to detect it. So you actually go to the best country in the world, which is Chile. Disclaimer, I am Chilean. And, Chile is a country, really long country in this, South America. And just going to give a brief, summary of Chile. Chile hosts almost, at this point, 50% of the ground-based telescopes of the world. They're located in the Atacama Desert. But because of time, I can't talk about all of them. But I can talk about the tree map of exports of my country. But I just will go to the straight point. The best thing we have ever exported is Pedro Pascal. If you didn't know, Pedro Pascal is from Chile. So the best thing we have ever exported, besides, of course, astronomy. And because Pedro Pascal is so important, I'm going to use him as a measurement for, comparison size of my telescope. So if you go to the north of Chile, you're going to find these telescopes that are at almost 5,200 meters over the level of the sea. Again, this is really high, 5 kilometers over the level of the sea. You're almost outside of, Earth. The atmosphere is so low that you can actually see the origin. This light comes from the origin of the universe. And that's where the Atacama Cosmology Telescope was located and took the most precise image we have from the early universe. And it was located 40 kilometers away from a town called San Pedro de Atacama, if you have ever visited. And it's next to Alma, which is also some radio telescopes there. And that's Pedro Pascal for reference. And if we zoom in to the side, this picture, I took it like less than a year ago. You will see there's no telescope because the telescope ended up taking data only a few years ago. And that's Pedro Pascal also for reference. But the amazing thing about this telescope is the improvement on resolution, because we were in Earth, we can make even bigger telescopes. This was a 6-meter telescope. And that was able to, improve the resolution from space to this. And we're finding so many, information that we're not able from space because we were not able to build such a big telescope. So in other words, it's like looking at space in a much higher resolution. And my colleagues are going to be talking about those really special dots that are there. Because of time, I'm just going to finish with the state of the art. So as I showed you, this telescope is no longer operating. And now we have something much more advanced, which is the Simons Observatory, which is also 6 meters. It's a collection of 7 telescopes. And my other colleague is going to be talking more about the instrumentation of them. But Pedro Pascal for reference, this is a large aperture telescope. And there's other 7 small aperture telescopes, all located in the same site. And they're revolutionary in our field. And they're allowing us to really, really understand in detail the origin of our universe. And my colleagues are going to be talking more about this. But I really, really hope you have enjoyed this teaser of what is our understanding of the origin of our universe. Thank you so much. So the question was, in the future, what will happen to the cosmic macro background? And the answer is, indeed, if the universe continues expanding, that's what we should expect. If the universe decides to contract, it will switch to the other way around. Our observations of the cosmos have been hinting us that this expansion should continue, but we need more data, and it's hard to really predict the future. We can predict more or less the trend, but that's an active area of research. Really, really good question, though. It's really interesting. So the question is, the light particles from this early light, do we find like places that we don't find some of them? Is that the question? So if I understood the question, what we're finding is that it comes from, it's like the whole universe is filled with these particles of light. So if I move somewhere else, I would also receive this light. but we're stuck here in Earth, or at least in our neighborhood. So one of the things we assume is something called the cosmological principle. If we don't believe we're in a special part of the universe, all of these particles would follow this kind of shape, and it's exactly what I was saying. There's people theorizing of maybe if I move farther away, I'm going to find a different cosmic micro background. And if that's the case, our assumption of the cosmological principle is wrong. But it's a really interesting thing. And there's people trying to find also evidence that break that rule. So yeah, and if we actually solve it, I wouldn't have a job. So it's good to have open questions.
Thank you so much. Yeah, so thanks, Bernie, for that really great introduction to the CMB. I'm going to be talking now about the science goals from the Simons Observatory. So again, this is a really nice picture taken of the site. And Alex will be telling you more about the actual instruments. But you can see in the sort of background there, I don't know if I can use the pointer, that is the large aperture telescope that Bernie was telling us about. And then we also have several other telescopes which are in these shields. And these are called the small aperture telescopes. So these are very different instruments. We'll hear about them from Alex, but I'll be telling you a bit about how they're working together, looking at very different aspects of the sky in order to answer some of the biggest questions we have about the beginning of the universe. So there's lots of goals from the Simons Observatory, and I'll just focus on a few of them. And one question that we're really trying to answer is sort of a series of questions. So I'm going to ask these three questions. Bernie told us that the universe is expanding, but what started this expansion? A different question, which might sound unrelated, is what sourced all the structure in the universe? And another question, which again sounds unrelated, Bernie told us that the universe is the same in every direction, and why is that the case? So these questions are actually, in some sense, all connected, and I'll tell you about how we're trying to answer them. And then later on, I'll talk a bit about how we're trying to understand what the universe is made of. So we think it's made of dark matter, and I'll talk a bit about what that might be. Okay, so yeah, these again are the big instruments we're using to answer the questions that Alex will be telling you more about. Okay, so here is the history of the universe that Bernie was also telling us about. And there's lots of different phases. So the universe has looked very different at different times. And at these times, different physics has been important. So there's sort of a big section in the middle, which is from before the cosmic microwave background was released. And here we actually understand pretty well what's going on, because here we've actually extrapolated the physics that we can understand from experiments in the lab to what the universe would have looked like when it was very hot. And we think that that describes this part of the universe very well. But before, and after that, this is when the CMB was released. But before that, we're actually not sure. So something happened at the very first fraction of the second to start everything. And we call this inflation, but we don't really know what physics it could be. So this is not physics that we can understand by doing experiments on Earth. And again, there's also a mysterious period at the end of the universe where dark matter and dark energy have become really important. So these are sort of regimes, very different regimes of the universe's history that we're trying to access with data from the Simons Observatory. So this thing that we think might have started the universe is called inflation. And this is what we think could be the answer to these sort of questions of what started the universe's expansion and why there is stuff in the universe at all. So I'll tell you a bit about how that works. So I have this little picture of what the universe, what space looks like on really small scales. Unfortunately, the saturation is actually not very good on this color scheme. I apologize for that. But what we think happened with inflation, which lasted a really, really tiny fraction of a second, is that the universe went from being extremely, extremely small to being extremely large. And when we think about things that are extremely small, we're thinking about physics in a very different regime to what we're used to looking at, even in this room. So on this regime where things are small, we have something called quantum physics. And quantum physics is this very strange world where, we don't really, we have math that tells us what's going on, but it's really hard to have an intuitive understanding. But one thing that's really, really important is that on these very small scales, we have these mysterious things called quantum fluctuations, where all the structure that you could possibly think of is sort of randomly popping in and out of existence. So this is what this sort of cartoon is supposed to show. So during inflation, what happened is a really, really tiny microscopic portion of the universe where all this mysterious quantum weirdness was happening got stretched to being much bigger. So if we go from something that's trillions of a trillionth of a trillionth of a meter, so extremely small, up to a few centimeters, so something that's sort of the size of a marble that you can hold in your hand, but over a really tiny fraction of a second. So this is a really, really big stretch in the size of space-time. And you can think of the analogy between these distances is a few centimeters would get stretched to the whole size of the universe within the same amount of time. So this is really, really a fast expansion. And this can answer these questions because what we have is a universe where everything that's close together and can sort of look very much like each other now gets stretched to being the same everywhere, which is why we think the universe looks the same everywhere. But perhaps more mysteriously is that these mysterious quantum fluctuations actually evolved into all the structure of the universe. So we have a universe that starts off with these sort of random quantum fluctuations that are frozen in, and then we evolve them. So it takes 300,000 years for the CMB to get released. And over this time, what we have is physics that we understand. So gravity, for example, grows these little tiny fluctuations so that they turn into these small fluctuations that Bernie was telling us about in the CMB. So these are still very tiny. We saw Bernie's sort of saturation image that these were super, super small fluctuations. But if you give that more time, so we live in the universe today when it's 14 billion years old, these tiny little fluctuations in temperature actually evolved into being these galaxies that we see in every direction as well. So because of these tiny fluctuations in this small patch of space-time, this is why we have structure in space. But what's interesting is that space isn't special. So this is actually a possible explanation for why we have structure at all. So why we have, you and me in this room, why everything isn't the same at all, could be due to these interesting quantum fluctuations. So this is sort of a theory that we think could explain why there is structure, but we don't really have good proof for this. And this is something that we're looking for in the polarization of the cosmic microwave background. So you might be familiar with the idea that light can be polarized. And the idea here is that light is a wave that oscillates, and so it can oscillate up and down and side to side. But if it oscillates preferentially in one direction, we call that polarized. So here I show that light, if you put it through these slits, starts getting polarized in one direction. And what we can do with our SATs, our small aperture telescopes, is we can actually measure whether the light is polarized or not. So here, I show a plot of what we see with previous telescopes when we measure the polarization of this light. So here on top of these fluctuations, I'm showing a sort of direction in which the light is polarized. So this is actually the signal that we're looking for with these telescopes. And this can tell us about inflation. So there's sort of a standard signal that we see. So when we look at these telescopes, we see these sort of these lines that tell us about polarization. And when you look at these two options for what the polarization can look like, we see that the standard signal has a certain sort of pattern to it. So we have sort of sources where things are sort of pointing to and pointing away from. And this is very different to what a signal from inflation would look like. So inflation would look like some sort of curly pattern that we see in the sky. So this is what we're really trying to measure. We haven't seen it yet, but this is part of why we're building this telescope. Okay, but this is going to be hard to measure. And the one reason that it's hard to measure is that when we look at the CMB, we don't just see a clean signal from the early universe. So the CMB is actually passing through a lot of structure before it reaches us. So in this sort of second half of the universe, we have a lot of stuff going on. So here I'm sort of stretching this out because it will make things clearer. And what we see here, as we look out from today, is that the CMB is behind everything. And this means that the light is actually traveling through everything that we see and getting bent and interacting with all this structure along the line of sight. So this means that while the light is just emitted in every direction, what can happen is it can actually interact with this stuff along the way. So it can get bent, for example, gravitationally around these galaxies and lead to a different pattern in the sky. So to illustrate a bit how this works, I have a little cartoon where we have a sort of background CMB that's emitted. And if there was nothing between us and the CMB, this is what we'd see. But in practice, we have some structure. So if we have a really massive structure, it can actually bend the light so that what we see is not actually what's emitted, but we see this distorted signal. So we can sort of see these characteristic distortions in the light, and this is actually what we measure. And this can, lead to things that instead of looking nice and uniform, look pretty warped. And this, we call this CMB lensing. And this actually, what we call it CMB lensing because it does a similar thing to sort of what lenses can do. It can sort of warp the background light. And annoyingly, what this does is actually turn the standard polarization signal into a curly polarization signal. So this means that this can get in the way of the signal that we're looking for from inflation. And this is why we have a LAT. So, one reason why we have a LAT. So these are looking at very different signals to what the other telescopes look at. And one thing you can do with the LAT is actually look for these patterns, these sort of warping stuff in the CMB, and make a map of all the matter that has lensed the CMB since it was released. So this is actually real data from the Simons Observatory that's currently in commissioning, that's currently being taken and being sort of worked on for the first time. But what we see here is an actual map of all the matter in the universe between us and the CMB. So if you see here, we have these sort of dark spots and white spots along the line of sight. And where you see a dark spot, there's really more dark matter along that direction than there is in the white direction. And just for scale, you can see this is really a map of the sky, and this is sort of the size of the full moon for comparison. And I can see Ola in the audience, who's actually the person who made this map. So yeah, that's fun. So we can actually use this to undo the sort of confusion that we get in the polarization signal. So we measure with the SAT, and then we undo this confusion with the LAT observations. But what's really nice is that we can also use this dark matter map to do other cool science. So we don't know what dark matter is. We know it's there because we see that it warps the CMB, but we don't know what the dark matter is actually made of. We have some ideas, and different types of dark matter will lead to maps that look very different. So some ideas that we have are dark matter that is in some sense cold, and dark matter that is in some sense warm. So if dark matter is cold, we'll have this sort of very sharp pictures, and if dark matter is warm, we'll have these sort of fuzzy pictures. And the reason that this is happening, so if you imagine something that's hot, it's usually sort of moving very fast, and it sort of won't see stuff that gets in the way. So if you picture yourself cycling really fast on a bicycle, you're not going to see sort of small scale fluctuations. But if you're cold, if you're moving slowly, you can get trapped in these small scale fluctuations. And what we'll get is sort of dark matter that sees structure on small scales. So by making these maps and looking at what they look like, we can learn about what dark matter is. Another thing we can do is actually weigh neutrinos. So neutrinos are this other mysterious particle that we know exists. So we've measured them lots on Earth. And actually in Canada, they were able to measure the mass of do experiments that showed that neutrinos, even though they're extremely light, so for a long time, people thought they had no mass, and they were able to show, including Art MacDonald, who won the Nobel Prize for this, they were able to show that they do have some mass, but they're extremely light. So they're about 10 million times lighter than electrons. And another really important goal of the Simons Observatory is to weigh these. So depending on how massive the neutrinos are, we will have dark matter that looks very different. So if they're more massive, they'll sort of get stuck in these, or that they'll be able to escape these sort of fluctuations. And if they're very light, we'll see a lot of small scale structure in these maps. So this again is one of the main goals for building these experiments. Okay, so those were sort of the questions that I was focusing on, but as I said, there's other really exciting questions that we're addressing with the Simons Observatory. And a lot of these are actually to do with these interactions in the late universe. So here, I showed before that the light gets bent around the galaxies in the late universe. But what can also happen is we can have the light sort of reflecting off of the galaxies in the late universe, or scattering off the galaxies. So we can use that to light up the galaxies. And at the same time, the galaxies themselves are actually emitting light. So we see them in the data as well. So here is a really nice map from sort of the previous generation of telescopes that shows us why we can do this. So this comes from the Atacama Cosmology Telescope. And you can see in our data, as well as these fluctuations, you can see sort of these emissions from galaxies. And you can see these sort of point sources that are really sourced from late universe structure along the line of sight. And by studying these as well, a major goal is going to be to learn about how these galaxies got formed during cosmic history. Okay, so yeah, this is sort of more big questions that we're addressing. So things like how galaxies formed, as well as a bunch of other exciting goals like transient phenomena. So another thing that Simons Observatory is going to do is it's going to take a new map every single day, so we can see things that are there for a little bit of time and then disappear. So this is a really exciting new frontier as well. Okay, so I think that's basically what I have. I'll leave you again with this really nice picture. And again, this is sort of showing that, what we see in the sky is really in the microwave there above the telescopes. So yeah, thanks. Well, we're getting there. I mean, we're moving the needle. We're building these telescopes and we're doing this research. New money is always good, so we could build more telescopes and have less noise. So I think, yeah, in terms of something that can actually be done, more funding is always great.
Thank you. All right. Thank you, everyone. I'm very mysterious. Good. So we just heard a couple of really good talks. Thanks to our great speakers and my great colleagues. So Bernie gave us a little bit of a theoretical background about the Simons Observatory, and of course, Fiona told us about the science goals that the Simons Observatory has. So I'm going to talk to you a little bit about the telescopes that we use, the telescopes that we've built in order to make those science goals a reality. So my name is Alex, and I've been building instrumentation for the Simons Observatory for the past 7 or so years. So happy to take any questions later on if you want to corner me after the talk. So great, you've seen this image several times. The thing that I think we want you to get out of this is that it's a map. And in particular, it is a heat map of the early universe. So we call it the cosmic microwave background, of course, because as Bernie said, comes from the cosmos, it's observed in the microwave, and it's everywhere. It's the background of the universe. But importantly, it's a heat map. So wherever you see red splotches on this heat map, that corresponds to things that are sort of hotter, and blue things correspond to things that are colder. So of course, because this is in the microwave, and we can't see microwaves with our own eyes, we have to build telescopes that are capable of seeing this kind of light. So we are capable of doing that in the modern day, which is kind of an extraordinary thing. Okay, so whenever we are trying to look at something, be it the person next to you or the cosmic microwave background, you want to have a very clear line of sight to the person next to you or to the cosmic microwave background. If you look to the person next to you and there's a cloud in between you and them, you're not going to have a very good view of the person next to you. So similarly, we say that water is the enemy. We hate water. So what we try to do is we try to go as far above the water that's in the atmosphere as we possibly can. Typically, you hear these big experiments go to space. If they're capable, if they have a lot of money, they're able to go to space. They strap their telescopes to a rocket, they send them up, and then they never have to deal with clouds ever. We don't have that luxury, unfortunately, both because we don't have enough money and because we have very, very, very large telescopes. And that's a very difficult thing to send a telescope to space. So we go for the next best thing, which is go to Bernie's home, which is Chile. So in the north of Chile, we have the Atacama Desert, which is actually the driest non-polar desert in the world, and let's go there. So this is a great video from some of our other collaborators. We're right on the border with Bolivia, on top of a mountain called Cerro Toco. It looks kind of Martian. You'll see in the images that are upcoming. Great, so there's our site. It's very red. You're gonna see the LAT, the SAT. There's a lot of acronyms. We'll go through them. There's a PVA, which is a photovoltaic array. We're actually gonna be the first solar-powered CMB observatory, which is awesome. So good. So this white building that you see here overlooking the plateau is our large aperture telescope, LAT, large aperture telescope. So this is actually a behemoth. It is 15 meters tall, 15 meters wide, and it moves, which is crazy. We have a bunch of these small aperture telescopes, which are significantly smaller, but are also sort of marvelous pieces of engineering. And I work on the LAT, so I'm going to primarily be talking about that, but the small aperture telescopes are sufficiently similar that you'll learn about them just from me talking about the LAT. So again, we're on Cerro Toco in Atacama, Chile, and we're at 5,200 meters above sea level, which is more than 700 meters higher than the peak of Matterhorn. So we're very, very, very high elevation, which means when you're at the site, you have to wear oxygen. Otherwise, you're going to have a very bad time. So good. So we have two different kinds of telescopes. We just learned in the last talk that we have different science goals for different kinds of telescopes. So for the large aperture telescopes, we have a very narrow field of view. We get to look at the map of the CMB, the cosmic microwave background, and resolve very, very small features. And there are many, many science goals that it pursues. The small aperture telescopes instead have more of a wide field of view. They look at wider scales, and they have sort of coarser resolution, which are purpose-built to see this polarized light that we just heard about a moment ago. But the thing that I want you to get out of this is that they're not telescopes that are just, they happen to be sitting on the same mountain. They are complementary telescopes. They're built to work with each other. So that's exactly what they do. Okay, so this is our site. You can see that there is one large aperture telescope to the left, and then you have 6 small aperture telescopes sort of distributed around the site to the right. So again, I'm going to mostly talk about the large aperture telescopes, but I'm going to breeze over what the small aperture telescopes look like. So they look like that, which is sort of a complex instrument. It's a complex machine. You have a person, which looks a little creepy off to the right. But these telescopes are on a platform, which is also sort of a robot, and it moves around. And they're surrounded by these shields, which are called ground screens, and they're basically there to stop light from the ground and other things from coming into the telescope. So if you look at the heart of this thing, you'll see a camera. It doesn't really look like a camera, but it is, trust me. And if you cut it in half, you're going to see, you are not going to be able to see anything here, but I can assure you that we will go into more detail in a moment. There's sort of a lot of gold and a lot of complex machinery in there. We'll talk about it more in the context of the large aperture telescope. So these are the small aperture telescopes working on sky right now. They're observing, and they're doing a fantastic job. We have 3 of them that are operational right now. They came from the US, and we have an additional 3 more which are being developed by Japan and the United Kingdom. Okay, great. So back to the site view. There's the large aperture telescope. Wow, what a great picture. That's really nice. That's from Dave, who's one of our site crew, and he's fantastic. We have a permanent staff of people that work at the site, and they're sort of critical to this mission. Okay, so if we cut the LAT in half, let's blow that up. You're going to see it is huge. As I said a moment ago, it's a behemoth. It's 15 meters by 15 meters. And it rotates. So it rotates about 2 axes. This thing that just popped up on the screen shows you where one of the axes is. So it rotates like this. And then it has an elevation structure, which is the thing that's highlighted in red, which also rotates in this direction. So this thing moves around like crazy. So it's kind of an amazing thing to see this happen live. All right, so inside this elevation structure, we have 2 mirrors. We have a primary mirror and a secondary mirror, 1 and 2. So when we take light, CMB light from the sky, put it on the primary mirror, it gets reflected off, hits the secondary mirror, and then is focused into that white cylinder thing. That thing is, for context, that's Pedro Pascal. Very, very large. That is our large aperture telescope receiver. It is called a receiver because it receives light from the sky. It's just a camera. That is our camera. So this is one of the more beautiful pieces of engineering in the history of our field. And I'm not biased. This is the Large Aperture Telescope Receiver, or camera, the latter. So to give you context for how a camera in the microwave works, I'm just going to flash this up on the screen. So a map of Canada, which is a very big place. You see a lot of different ranges of temperatures across the country all the time. You know, on a typical, whatever, Sunday, I don't know, what day is today? Tuesday? I don't remember. It's an average of 23 degrees Celsius, say, across the country. I don't think that's true for today. But you'll see that there's sort of a large range of temperatures across the country. If you instead look at the map of the CMB, which you've seen multiple times already today, it is remarkably uniform. And it is also remarkably cold. When we say negative 270 degrees Celsius, we really mean negative 270 degrees Celsius. That's incredibly cold. And the more remarkable thing is that it's incredibly uniform. So unlike Canada, which is also really big, something that is the size of the universe effectively is so remarkably uniform. Negative 270.4242 versus 4248 Celsius. That is a very uniform map of a place, right? So in order to measure the changes in that map, the changes in temperature between one place and another, you have to have a camera which is sensitive to those changes. So the way that I like to think about that is if you were to go outside on a sunny day, you close your eyes and then you put your hand up to the sky and you try to find where the sun is, you will actually be able to do so pretty well. And the reason for that is because your hand is colder than the sun by a lot, which means that your hand is sensitive to the heat light from the sun. Right? So your hand is a very good sensor to determine your location with respect to the sun. If you were to do the same thing at night, you close your eyes, go outside, and try to find the moon, you won't be able to do that. And the reason for that is because your hand is hotter than the moon. So in other words, if you want to measure something that has a temperature, you need to be colder than the thing that you are measuring, which means we need to be colder than negative 270 degrees Celsius, which you might say is like, okay, how is that possible? Our cameras have to be refrigerators, and they can't just be regular refrigerators. On the topic of home appliances that Bernie brought up earlier with microwaves, they literally are refrigerators. And we have to cool our cameras to negative 273.1 degrees Celsius in order to even measure the CMB, in order to even think of measuring the CMB. And we do so. And this is actually, believe it or not, 0.05 of a degree above the coldest possible temperature. Before I joined this field, I didn't even know there was a coldest possible temperature. But here we are, and we've built a machine that can do that. How do we do it? It works actually remarkably similarly to your actual refrigerator. We swap the coolant from Freon to helium. Let's get back to work. Okay, so the receiver is this huge, huge thing, 2.5 meters by 2.5 meters across. You cut into it like a birthday cake. You see that gold chandelier in the back? That is our helium refrigerator. So that thing actually delivers our cooling power to the rest of this instrument. It is a 7,000 kilogram cryostat. So this is a huge, huge instrument. You have to cool a lot of mass down in order to do anything. You're going to see these tubes. There are a bunch of these tubes, which I'm going to blow up here. This is really where the magic happens. So you get light from the outside world. It goes into this tube, and then it is incident. It hits these what we call focal planes, and that's where our detectors live. All right, and that is what we have to cool down to negative 273.1 degrees Celsius, which is just a fraction of a degree, again, above the coldest possible temperature. So we have the 7,000 kilogram cryostat with a 15 meter by 15 meter telescope, all to cool down just 200 kilograms of mass to this very cold temperature, and we do it. So light enters through, our telescope, hits the primary, secondary, focuses into the telescope, and then it hits our focal plane, and that's where the magic happens. Great. So yeah, you have all these little thermal fluctuations, these temperature fluctuations in the sky and the microwave, and we're able to measure them because our detectors are sensitive to 0.00001 degrees Celsius temperature changes, which is a pretty remarkable thing. But that's the only way we can do it, and that's how we do it. And basically, the way we do it is by having these detectors, which are all effectively thermometers, and these thermometers, as I said, are sensitive to that tiny little number. Okay, great. So here's the overall summary. You have light focusing into the camera. Pedro Pascal is always there. You have this big camera, which has some extraordinarily cold thermometers in it, which can measure the sky. And we have 13 of them. We have more than 60,000 of these thermometers to measure the sky, which makes it the most sensitive instrument ever built to measure the CMB. Okay, this was 7 years ago. This is when I first started on the project. That's what the camera looked like then. These are some of our great graduate students. And this is what it looks like now. So it is a remarkable amount of work that went into this and sort of a remarkable feat of engineering. There's the receiver at the site with our telescope. This was a very nerve-wracking day when we lifted it up. And this is us lifting our optics tubes, which have our focal planes in them, into the receiver. This is an insane thing that we do, but it's actually a lot of fun. And it's incredibly nerve-wracking. Okay, and here's the telescope rotating. This is a very incredible thing that happens. Again, this is like a 4-story building that's moving. And of course, this is a big time lapse, but it does move pretty fast. Something that I have on the bottom is you have to keep in context that we're at negative 270 degrees on this thing. And when things move, they tend to heat up. So it's kind of a hard problem to keep it as cold as it has to be while it's moving so much. Okay, so last slide. How are we doing? We have a great team, both for the large aperture telescope and the small aperture telescope. This is certainly not inclusive of everyone, but they all deserve a ton of credit. So this is a map that our predecessor experiment took, the Atacama Cosmology Telescope. We heard about that briefly before. It took 5 years for them to get a map with this kind of resolution, that kind of sensitivity. And I'm going to show you exactly the same map of the same patch of sky of what we did in 6 days. So that took 5 years, that took 6 days. We basically are matching what they did in 5 years in 6 days. So you can imagine over the next 10 years how well we're going to do. So we're very excited for it. And I just want to say we're going to be on solar power soon, so it's very exciting. Okay, thank you, everyone. So we are only at the moment sensitive to the inflationary period in our small aperture telescopes, not our large aperture telescope. But yes, we can measure the inflationary epoch by inferring some information that we get from these maps that I showed you. And we can only see into our own universe. If you're asking about other universes, we're not quite there yet. But, we'll see.
Okay, everybody, we're going to get started again. Awesome. Okay, great. Thank you. Okay, so my name is Simon Nerval. I'm a PhD candidate here at the University of Toronto and Dunlap Institute for Astronomy and Astrophysics. I'm going to be the panel moderator today. In terms of the type of work I do that's relevant for the Simons Observatory is I've worked on trying to clean our data, get rid of weird electronic stuff, and also find those cool transient signals that Fiona mentioned. And then I also look at different models of inflation and use computers to figure out what signals they would produce, and then figure out how well we can constrain that with the data that we have. I'll pass it off to the panelists to introduce themselves as well.
Sure. Hi, my name is Ellie Shaw. I am a postdoctoral researcher at the University of Texas in Austin. I currently work a lot on the small aperture telescopes, doing some instrument deployments and making sure that they got built and deployed. And I also work on the pointing models, which means that making sure that we know exactly where the telescopes are pointing.
I'm Tony Merchkovsky. I'm at the Institute of Space Sciences outside of Barcelona, near Barcelona. I'm an instrument scientist. I'm more senior. I basically want to build next generation instruments and look at some of these structures like galaxy clusters and things that Fiona mentioned in her talk.
Good evening, everyone. My name is Simon. I'm a postdoctoral researcher at the University of Manchester in the UK. I mainly work on the data analysis part for the small aperture telescopes, and I develop new algorithms to try and make the most out of this wonderful data that we have.
I'm Carmen. I'm a PhD student at the University of Cambridge, and I work on the measuring and extracting science for from the sort of signals that Fiona mentioned in the second part of her talk. So sort of the interactions of the CMB with the matter in the universe all the way to us.
Great, thank you. So we're going to start with one or two of the pre-submitted questions, and then we're open it up to get questions from folks here. Okay, so to start, the question is, to measure the cosmic microwave background, how do you filter out the other sources, such as stars, galaxies, and then even the Earth's atmosphere? Whoever would like just to start that off, feel free.
I'd love to. So for the sources, we observe in 6 colors. So for comparison, our eyes see 3 colors generally. The human eye sees 3 colors. And we can distinguish colors, you know, like if you have a red background, you can see something that's green. So, you know, by analogy, in our 6 colors, we would see a galaxy as something, you know, more blue, more bright, you know, and sort of a hotter temperature color than the CMB in general. So you can pick things out that way. And radio tends to be redder. They tends to be lower energy than the CMB. So you can pick that out. And then for the atmosphere, we actually take advantage of the atmosphere always changing. You know, every second, like the atmosphere looks different. So as we scan around, you go back to the same point and you see this change and you try to sort of subtract that out from your signal and make a map. And we do the best we can, but that's a dominant source of noise when we're making a map. But, yeah.
Great. Did anybody else want to add anything before we go to the next question?
Okay. That was a great description.
Yes, it was. Okay, the next question is, how do things like our stars and galaxies and the structure in our universe form?
I think Fiona explained this very well, and actually, starting with the small quantum fluctuations that she presented, actually gravity evolves them and makes them grow slowly, one falling into each other, creating the first stars, and from the first stars also falling into each other, first planets, galaxies, all the way to the structure that we know today. So it's a very sort of hierarchical process, starting from the smallest fluctuations all the way to the structures that we know today.
Right.
Yeah.
Okay, so the next question, I think maybe we'll start with Ellie answering about more about how an instrument works, since you're more on that side of things. So for the next frontier of telescopes, and I guess including the SO's new, so also for SO, what is it doing differently than previous ones that's making it so much better?
That's a good question. Something that plagues telescopes that are on the ground, like when our speakers talked about, is the atmosphere and the water in it. And something that Simons Observatory does is have these big, gigantic sapphires that can actually rotate the polarization that the detectors see. And through some analyzation of that signal, of watching that rotating signal, you can filter out what isn't the atmosphere. So something that's changing day to day, the clouds. The thing that's constant is the CMB behind it. And so by modulating it, you can see what remains all the time. And so that's something unique that Simons Observatory, the small aperture telescopes do, is having those constantly rotating thing. And the reason why people haven't done it before is that it's very hard. It's I don't remember how many kilograms, maybe 20 kilograms of mass that's spinning at 2 hertz. So 2 times every second. So it's very heavy, and it's levitating on superconducting magnets that are at the temperature of liquid nitrogen. And so it's a very dangerous thing to have go wrong inside of something that you're keeping under vacuum pressure at very cold temperatures. So it's a very complicated technology that we've done. That's just one thing. Another thing is by having a lot of detectors. The more detectors that you have looking at the sky for as long as you possibly can, you can make more and more sensitive maps.
Great, thanks. Did anybody else have anything they wanted to add?
I guess I would just add that the number of detectors is enabled by having just a huge field of view. So we talked a lot about ACT, the Atacama Cosmology Telescope, and Simons really built a field of view that was just 60 times bigger, 70 times bigger. So it's transformative leaps.
Great. Okay, so one final question from the pre. Oh, sorry. Were you?
I don't know if they wanted to add more. There's a lot to say.
Yeah. From the pre-submitted before we open it up is if you think about different telescopes like JWST, are there any discoveries from these other telescopes that can be driving the type of science we're doing, and how can we, use the data from other telescopes with our data to figure out what's going on in our universe?
Well, this is a very complex question. So specifically for the JWST, it's not exactly looking at the same thing as the Simons Observatory, because it's looking at light that is a little bit shorter wavelength, and so it's looking at objects that are a little bit closer to us in the universe. However, as we have heard in the various talks, the CMB acts as a backlight for every all the structure that's in the universe, and so all the observations that are made by other telescopes such as JWST of the structure that's in between the CMB and us, we can kind of cross-correlate with these observations in order to say more about the universe than we could do from the single experiments.
I'll say that the large aperture telescope, since it has such huge mirrors, it can resolve very small features on the sky. And when events like supernova happen that don't last very long, that signal kind of changes in frequency. And what the Simons Observatory can do, since we're looking at microwave, there are other telescopes in the Atacama that are looking at different frequencies. And so if someone says, we saw this thing happen, everyone else can look at it as well. And so there's different people in our collaboration that are working specifically on those types of events called transient events that we can do that kind of science by collaborating with other also ground-based, not just space-based observatories.
Great. Anything else anybody wanted to add before? No? Okay, great. So does anybody have a question for our panelists? I'll bring the mic up for you. Okay, great.
Hi, so I'm just curious, what are you looking forward to the most once the Nancy Grace Roman telescope comes online? Oh, sorry. So the Nancy Grace Roman telescopes, the new infrared is going to be 100 times more powerful than Hubble's. So I'm just curious, what are you looking forward to in terms of science discoveries from the Nancy Grace? Thank you.
The Roman space.
Yeah. I don't know a whole lot about it. What I know is that I have a friend that gets to go watch the launch. But the Nancy Grace Roman Space Telescope is about to be launched at the end of August. It's a NASA project. And what I know about it is that there's a lot of science cases particularly looking at exoplanets. So looking for other Earth-like things in our galaxy. And so that's an exciting science case to think about how many other stars have planets circulating them. They're also looking into what the properties of dark matter are. And yeah, does anybody else know more about them?
Well, no, I don't know very much about the Roman Space Telescope, but I guess I would just add, in looking for planets, we can also stack our data and see a complementary signal from that and see something about the environments, that planets form in, see the Oort clouds around it, so the clouds of rocks and stuff that orbit around there, potentially. For dark matter, we're doing complementary probes of dark matter. So as a physicist, you want to test everything every way you can, and look at every possible tool so that you can confirm, and not just say like, oh, we answered it with this tool or that tool, but make sure you have a consistent picture, make sure you've done every possible test you can so that you really understand what you're looking at.
Great. Any other questions? Oh, I'll come back down in a sec. Was it okay?
Hi there. So I kept noticing in the diagram of the model of the universe that there's always a section called the dark ages. And so is that to be taken like literal, where there's not sufficient light for us to see anything and therefore it looks like there's nothing there? Or is there like an engineering problem with looking at that point in time, or some other type of challenge that is yet to be overcome?
Great question. So it's not an engineering problem. Well, mostly. So some people might disagree. No, but there is a real, let's say, scientific, physical, explanation for this name. So the Dark Ages are basically a period of time that's right after the emission of the CMB, and at that time, the first stars have not yet formed. And so there are no sources of light besides the CMB that's just in the entire universe, and this is why it's called the Dark Ages. So we have to wait a certain amount of time for the first structures and the first stars to form, for the first sources of light to appear.
I have a question regarding the telescopes locations, because there is a version that certain areas, like where those telescopes located, that might be a possibility of kind of like a portals or chrono corridors. How can you relate this question? So could be a portal to different dimensions. Do you understand what I'm saying? Like, because I personally heard, like, there was Atacama Desert, there were some contacts with aliens where, let's say, had a place. So my question is, why certain why those why they in a certain locations? Because those locations are very considered very like in a point like where those portals could be.
So I can only speak for myself here. I haven't had any direct experience with portals to other dimensions, but or corridors. But these sites are amazing in that they're super high up and super dry, and you can see through the atmosphere easily. And that's why we tend to build telescopes there.
In the place, and kind of you have in Chile, there are a couple of places I was feeling like I'm on a meeting. It's very interesting.
Yeah.
So just why is it certain locations those telescopes are placed?
We just go for the high and dry sites. Yeah, it's
A reason why we don't put telescopes in Bolivia is because the government is less structured. And so the Chilean government is a lot easier to work with in a policy and like getting infrastructure based. So that's the reason why we don't go to Bolivia. There's less infrastructure to work with.
Okay, the next question.
Hi. So for someone who's interested in breaking into the sort of like instrumentation, design, and engineering side of things, are there any particular specializations or expertise that you'd recommend developing? Like, I guess in the field right now, are there specific areas that are seeing a lot of motion, or is it kind of just everywhere is looking for more brain power all the time?
I don't know. Something that is interesting that's kind of related to your question is that the same refrigerators, the helium refrigerators that we use, are also used in a lot of quantum research, like in big tech companies. So in a way, like developing those refrigerating things is a big technology thing that helps both science and I guess they're both sciences, but yeah, I don't know. I think getting into optics, like simulating how the light moves to the telescopes, is always a really interesting thing that helps you better characterize your instrument so you can make more sense of your data. I think basically every small thing that's in our telescopes, I don't think we mentioned it. There's over 500 people that work on the Simons Observatory. So there's enough people that people can have very specialized jobs. And so I would say there's someone working on almost every single aspect, from making those sapphire things spin perfectly to making sure that we don't see the vibrational heating of the detectors, like Alex was saying. So basically every single thing you could think exists on the observatory is something that people can like work on making better.
Yeah, if I can reinforce that, yeah. I guess we're working on the optics. I would also say, understand the electromagnetics, like really understanding, we use a lot of filtering of our signals to clean up the signals. So understanding electromagnetics of filters and waveguide structures and microstrip structures and all of that. So really knowing the electrical engineering of that. We have to digitize our signals. So you have to record the voltages at very fast rate and digitize that, and then deal with the data, and map that. And you also have to deal with just very large data volumes. And as we build more and more detectors, we have to deal with that. So knowing digital signal processing and then knowing how to deal with that computationally, there's every aspect you can think of. And then, these spinning superconducting, maglev plates, like really understanding that and understanding how to make those work. And, also just the more plumbing aspects, like, when you to cool something, you have to make sure it doesn't leak, and that you have like, that your cryogens work and all that. And yeah, I just was reinforcing things. Yeah. But there's every aspect, I guess.
Great, thank you. Okay, I saw that hand first. I'll go there. I'll go around the back. Hand it to you.
Yeah.
Sorry.
I just want to hear a little more about like the process of planning and developing the telescopes. Like, how did the idea for those telescopes, like the structure, the spinny, like how was it decided, like which aspects of scientific research was put into it? And then was the research like mature, or was it specifically matured for the telescope?
Do you want to answer it?
I could try. Then someone can follow up. So that Bernie showed a lot of pictures from the Atacama Cosmology Telescope that has stopped observing. A lot of the people that were working on that experiment now work on Simons Observatory. A lot of people that worked on the previous experiment worked on a different one. And so a lot of the technology has developed and gotten a little bit better every time someone builds a new telescope. And so there's also telescopes doing the same science at the South Pole. And so they might come up with a better way to do the filtering or create a better window. And so sometimes it's not just someone says, we should try this. It's, oh, we tried that, it didn't work as well. Let's make it better.
Yeah, so it's evolution of previous things in a lot of ways. And I think Fiona or maybe Bernie showed the pictures from New Jersey. Yeah, Bernie showed the pictures from New Jersey, where it just started with a really simple giant feed horn looking at noise, right? You know, so like we evolved from there, and you know, every new generation brought a new clever idea that improved things. So yeah, it is really evolutionary.
Okay, so we have time for one more question, so I'll put it over here.
So it seems to make the CMB, you need to look at all directions, and intuitively that makes me think that there should be a telescope on the equator so you can look at all directions of the sky.
Well, we actually, well, that's true. One of the bad things about not being in space is that you only have access to a restricted section of the sky. Depends on what you want. You might want to look at a very small section, just very deep, and decrease your noise. In our case, that's one of the reasons we have the large aperture telescope, is to try to maximize the amount of sky we look at. We take our telescope shifts, as you saw, but the Earth also rotates. So that means we can actually look at way more sky than just what you see. So we take into account both of those things. That's why pointing is actually a very hard problem, more than you would think, to actually know what you're actually looking at, because there's so many rotations to take into account. Yeah.
Great. Okay, thank you. So thank you all for answering all of those questions. And a lot of SO people will be staying around if you want to talk to them, but let's thank our panelists.